Hi, my name is Pablo Zegers. I'm the Vice President of Product of a company called Anastasia. And today I'm going to tell you what we're doing in order to democratize the access of artificial intelligence for many companies in Latin America and hopefully in the world. All companies need AI, but not all of them can access it. So it needs to be democratized. And this is the main goal of our company. Anastasia was founded in 2017. We are currently 32 employees and hiring. We have offices in Chile, where we started. Then we expanded to Mexico. We have our offices in Monterrey, in the northern part of Mexico. And now we are preparing to land in the United States, where we think we can offer our products successfully as well. We're active in three different industries, mainly retail for now, but we're trying to expand in the supply chain vertical. We're actually building all types of solutions around the supply chain problems and adding artificial intelligence into them. We have 12 clients and we're growing, expanding in Chile and Mexico and preparing to expand in the States. Anastasia was founded, as I told you, in 2017, and we started as a consulting firm, strongly focused on providing tailor-made solutions for our customers. But with time, we pivoted and we realized that there is an opportunity for building an awesome product based on artificial intelligence, which is what we're doing right now. We are capitalizing on the AI talent that is present in Latin America, but that cannot be used by companies because they are lacking in culture and leadership. So they cannot use it in order to build or redo or transform their internal processes in order to use the advantages that artificial intelligence provides. The focus of Anastasia is in small and medium-sized companies. Why? Because most of the large companies already have services and products useful for them. Moreover, they have internal and very strong teams with lots of data scientists that are capable of handling artificial intelligence, understanding it, and using it in benefit of their companies. On a stark contrast, even though small and medium companies are almost 90% of all the businesses of the world and capture 50% of all the employment worldwide, even though there are more than 150 million of them all around the planet. I put that figure 150 because it's the lowest I saw. But there are even larger figures that it's difficult to capture, to measure them, to count them. I've seen figures that say there are 700 millions of them. So I settled for the lowest number I could find. But the problem is that they do not have the internal culture. They do not have leadership. They do not have access to talent. Or simply they don't have the money that's needed in order to build an internal team that's capable of dealing with artificial intelligence. Hence, even though they need it, they cannot use it. So this is a huge, huge opportunity that's waiting for somebody to grab it. Even though they cannot build these teams, they are eagerly waiting for somebody to give them tools that translate their data into business results that increment their sales or reduce the costs, their operational costs. They don't care about what happens in between because they don't have the capacity. They don't have the people. They don't have the knowledge on how to lead very technical teams. Or even worse, the only thing they know about is their business process. and they don't care about technology because they don't have educated people in terms of technology within their companies. So basically, they cannot jump into this huge opportunity. And that's the goal of Anastasia, is to provide them with these tools. Just to put some context, a large company can handle, for example, hundreds of thousands of products, SKUs, as they are called. But a small or medium-sized company can have hundreds or thousands of SKUs. So there is a scale down size of the type of operations they typically run. And that means that it's even more stringent because we have these companies that need artificial intelligence. They don't know about it, they cannot handle it, but they need it. And still, their operations are smaller. So they cannot spend as much as a large company. So it's a very tough problem because it's a smaller problem under very serious financial constraints. Well, in order to solve this, Anastasia is building a platform with the following philosophy. We think that artificial intelligence is going to be like cars. Everybody uses cars, but almost nobody knows about mechanics. Well, artificial intelligence is going to be probably the same. It's so complicated. It demands so much specialized talent that it's going to be beyond the capacities from the reach for most of the companies. So they are going to use prepackaged modules, products, services that embed artificial intelligence, and so that they can focus only on their businesses. Well, our platform is created in a way that it can build solutions very quickly, so we can adapt to the different needs of the different business processes we're encountering as we are expanding. And each of these solutions is embedded with artificial intelligence in a way that the companies don't need to know that there is even artificial intelligence beneath it. They only need to focus on the business results. Just get the data in and produce the results and use them. Take them to whatever action you need to take in your business. Now, this is huge. Building solutions for the many business processes that there are in all SMEs in the world. SMEs are small and medium enterprises. It's so huge that we decided to start focusing on the supply chain business vertical solutions. Currently we're just doing demand forecasting and supply prediction. These are two very important ends on the supply chain process. And this is currently our focus. We want to do the things well in this and start expanding in other aspects of the supply chain problem and in other business verticals as well. So now I'm going to start with the topic of our presentation, time series forecasting. There you have a plot where you have black lines. In the black lines, you see a trend, a very consistent line centered in all that noisy signal. And superimposed to that signal, you have noise. And this is the reality we see in all time series, in all customers. Time series are composed mainly of two components, a deterministic one and a stochastic one. The deterministic one can be handled by mathematical equations, but the other one corresponds to random processes. It's like throwing a dice. You cannot tell whether you're going to get head or tails in a coin, but you know that you are going to get either head or tail. So the same happens with the time series. The customers know that they cannot predict very well what's going to happen, but they want to know the range of those predictions. To make things even worse, this can be corrupted by missing data, wrongly measured data. You have that all time series are different. In a customer with 10,000 SKUs, All time series are different. Some of them are densely populated, others are very scarce. So each of them has to be treated in a unique way. Forecasting for these customers, even though they're small and medium enterprises, needs to be very precise because it's even more critical for them. You cannot hide errors in large numbers. For example, we have a customer that has only 90 products. So a huge deviation in the demand forecast in only one product can mean a lot in the annual balance. So we need to produce forecasts that are precise, fast, and cheap. It should be like breathing for them. Nobody cares about the air normally. Well, it should be the same for forecasting. So considering all of this, we need to build a system that takes into account the deterministic part and the confidence intervals, which are the ranges within which all the values are moving. But this is complicated. This is a paper that was published this year in June that exemplifies that in order to achieve very precise results, we are needing more and more computing resources. Because if we want to produce a very precise forecast for a client, we need to use everything we have. There is no compromise on that. But as all the environment in artificial intelligence is showing, this is exploding exponentially. We're having more and more powerful systems that are requiring exponentially growing resources. So we have to face this because our customers have very stringent financial constraints. To make things even worse, as it was shown in this other paper published in August this year, hardware is not growing exponentially. So this means that you have to use your infrastructure in a very efficient way. We're doing this using Ray and Anyscale, so we're pretty confident that we're using all the hardware we have in a very, very, very efficient way. But still, this is not enough. We need to do more. This is an example of what we're doing with the customer. This is one of our first customers. So this is not an example of a small or medium enterprise. This is a large company that sells around $4 billion a year. But in this case, we achieved between 30 to 53% of savings at SKU level. You see that the numbers change because all SKUs are different. But overall, we achieved a 75% reduction in the prediction error, which saves them more than $1 million a year. On the right, on the blue bars, you see the comparison we were able to do in order to prove that using SigOpt's hyperparameter optimization system was useful. So on the top bar, you have the overall error with SigOpt's system, and below it, without it. This allowed us, in this case, to reduce the error, the forecasting error. This is on the supply side of the supply chain problem of 11.79%. This is very important for us because in terms of the customer, it means that they're saving a lot of money. And in terms of our business, it implies a happy customer. If we had not used SigOpt, we would have not only more than 11% more of error, but we would expose our company to the competition, which may use, for example, SigOpt and offer better results than us. So this is also an insurance for us. It tells us that we're doing the best that can be done in the market with the best tools. But this is not the only problem. The other problem is the randomness of the results. And this is very, very important. In a recently published paper that addresses this problem for reinforcement learning, they show that many of the published results, which you can see in the colored plot on the right, they don't reflect exactly what's happening. On the rightmost plot, which is titled IQM, you see bars. The top 1 bars are the range of errors you get with 3 runs of the experiments. And in the lowest one, it's 100 bars. 100 runs. And you see tighter bars, tighter error bars. And this means that, like it or not, you need to train many times in order to have sort of an average system or results that really reflect what's happening. And if you don't do so, in our case, we run the risk of offering our customers forecasts that are not very precise, that can jump month to month. So how do we handle that? Let's analyze what happens with ExegBoost, which is a forecasting workhorse used by many. One of the problems in machine learning is the randomness of the entire operation. Why the randomness? Because the data that's used to train the systems, the data that's used to infer the results, is naturally random. Hence the randomness of the outputs. But in some models, like ExegBoost, the randomness also seeps in through the initial conditions, the random seeds of the algorithms. Every time you run them, even though you may have exactly the same data, produces different results. This means that the error surfaces, when you're training, when you're doing the hyperparameter searches, are fuzzy. It is difficult to characterize them. So the real importance of all the elements of the problem are obscured, and this makes it expensive to search for the hyperparameters and expensive to train, because what the system is seeing when it's searching for the hyperparameters, for the parameters, it's not very clear, because every time it runs the problem and changes the random seeds, gets different results. So what happens, for example, specifically in a forecasting problem with ExegBoost, when you're using SigOpt? The following. There you have, this is captured from SigOpt's interface. You have 1,000 observations of a very simple forecasting problem running ExegBoost. And you see that the system finally finds the right hyperparameters on the order of the 600th. The observation number 600, which is a lot. It's a good number though, below 7.9 in this case. But look at what happens here. The parameter importance. When you're driving a car on a windy road, the problem is fixed by the windy road. It shouldn't be fixed by the car. For example, if you have a very dark windshield, so you cannot see the road, that's a problem posed by the car. It's an artificial problem. The problem should be only the road. What you're seeing in the case of ExegBoost, all the parameters there, save for the one enclosed by the red box, are internal to the ExegBoost model. By the end shift is the one that in this case is saying how much data, past data, has to be watched in order to produce an accurate forecast. So this is like the only data, the only parameter taking care on how far should we see in this windy road is the end shift. All the other parameters are internal to the problem. It's like the car being the problem. And SigOpt rightly identifies that finding the internal parameters and the correct combination of internal parameters for ExegBoost is the problem. not N-shift. So the system is somewhat confused. What happens when we use ExegBoost to predict? Well, there you see on the right, on blue, you see a real data, and on the right, you see 100 different forecasts. Which one is the right one? For us, it's a nightmare because we know that every time we run ExegBoost, we will get a different forecast. So which one is the one we should handle to our customer? We have settled for the average, which is what you're seeing there as the green line, segmented green line, which has a certain error. But still, we don't know whether that's the best forecast. It could be a different one. There is no theoretical guarantee that that's the result we're looking for. So we're facing a challenge from the business perspective. The intrinsic randomness of the different learning machine models that are being used that makes them dependent on the random seeds, hence on the initial conditions, makes everything slower. Training gets much more difficult and increases costs. Moreover, the lack of certainty that the result is the best one adds operational risks for our customers because we cannot offer them a sure result, a result that we can guarantee is the best. And it makes it difficult for Anastasia to differentiate from the competition because if, for example, we perform a demonstration for a customer and we get some results, it may have been sheer luck that we got those results, and it could have been bad luck. And then comes somebody from the competition, but also by sheer luck gets better results. So that's why we developed our own recursive neural network, which is mathematically characterized to absorb these problems. There you see plots showing how our system is able to absorb initial conditions and behave in a very robust way. What are the implications of this? That when we run it in SigOpt, this is again captured from SigOpt's interface, the system quickly converges to the desired solution. There is a difference of scale compared to the previous plot, so that's not fair. But the important thing here is that in less than close to, I would say, 25 observations, we are right on the result. In the previous case, we were on the same level with 600. So that's roughly 24 times less observations. So having a system, a learning machine model that's able to absorb initial conditions allows us to perform at least one order of magnitude less to do the hyperparameter search with at least one order of magnitude less of resources, which is very important because that translates immediately in faster and cheaper results for our customers. Moreover, in terms of the importance, the relevance of the parameters, we see that in this case, SigOpt is not tricked by the fuzziness of the results. I quickly discovered that the delay, which is the amount of data we have to look for in the past in order to produce an accurate forecast, is the most important variable. So when you eliminate the intrinsic randomness of the model, SigOpt can work much faster, and we can focus quickly our machines into finding the correct hyperparameters precisely. Even more, when we run 100 different random seeds and we produce 100 different forecasts, we get exactly the same prediction all the time, which is the best prediction, which is the one you're seeing also in the green line there. But in contrast to ExegBoost, here the error is 7.93, where in ExegBoost the average, the mean was 8.2 something. So it is an improvement, but also we can guarantee that this is the best solution because the XRNN, as we call it, is totally mathematically characterized. So we know that we're getting the best result. And thanks to that, we have a much simpler training pipeline backed up with an efficient hyperparameter optimization, which ensures that we're focusing on the right parameters. And better, we can scale this up into very complex architectures, ensuring this behavior in all levels. Moreover, our system is able to, can be implemented in analog hardware because of the characteristics of the system. Now I'm going to switch to a different perspective just to close on my presentation, which is the environmental analysis. There is a paper now famous there on the left concerning, the title is On the Dangers of Stochastic Paradox. Can language models be too big? Which is a study on how models have grown so large that they're causing an important environmental impact that needs to be addressed. This is not a relevant aspect in a small or medium enterprise decision process, but definitely needs to be taken into account. Why? Because what I said, SMEs are just too many in the world. And as it is, artificial intelligence is not viable. As it was published in October of this year, it is calculated that by 2025, we'll get 5% of errors, some very important artificial intelligence problems. But this is going to require a CO2 production that's equivalent to that generated by the entire city of New York in 1 month. That's ridiculous. And if we continue producing the same amount of CO2 for all companies at this rate, forget about SMEs. This needs to be solved first. So, considering that in the world there are around 150 million SMEs and more or less 700,000 large enterprises, that implies a 214 to 1 ratio, assuming that SMEs, the artificial intelligences running on SMEs, are 1/10 in size or in computational resources to that used by the large enterprises. The SME segment in the world would contaminate close to 20 times more than large companies. So if we are going to offer artificial intelligence to SMEs, small and medium enterprises, all around the world, we need to at least improve in that order of magnitude the efficiency of our artificial intelligences. If not, this is going to be ridiculous. It's going to be impossible. And that's what we have shown today in our presentation. First, using business knowledge, using hyperparameter searches, using ray and any scale, we are able to run a very efficient operation. And with this XRNN model, we can even go further, several orders of magnitude. And with this I finish. Thank you very much.